Welcome to The Explainer. Today, we're exploring a pretty fascinating paradox in the world of artificial intelligence. We're really unpacking the core focus of episode 25, which is exactly why raw computational intelligence, the kind concentrated in a single, highly capable model, just isn't always enough for complex, long-horizon problem solving.
Okay, let's dive right into this. Can a highly intelligent AI actually lose to a team of weaker systems that continuously check one another? I know, the answer counterintuitively might actually be yes. Naturally, we assume that the strongest, most capable individual model should just automatically produce the best results, right? I mean, if one system reasons more accurately, understands more concepts, and solves harder problems, why on earth would we choose to divide the work among several less capable agents?
Well, to understand why, we really need to reframe our baseline assumption about intelligence itself. Think about the single mind. It's characterized by this crowded, tangled reasoning trapped inside a limited context window. Now contrast that with organized intelligence, where reasoning is cleanly divided and structured across multiple agents. The reality here is that intelligence isn't just about how well a system reasons at one single isolated moment in time. It's equally about how much structural integrity the system can actually preserve across time.
Section 1. The limits of the single mind. Let's break down exactly why this happens.
Now, what's really interesting here is how attention mechanically degrades within a single model. A single model has to operate within a limited context, right? It takes in information, processes it, and spits out a response. And while modern attention mechanisms are theoretically amazing at connecting distant parts of a prompt, look at what happens as the context grows. Step 1, early assumptions are made. Step 2, new data just floods the context. By step 3, those older facts actually begin to fade in influence. And finally, contradictions go completely unnoticed because important details are just displaced by more recent or prominent information. So the system technically receives all the data, but it absolutely cannot use all of it equally well.
Sure, a single model might perform flawlessly on a difficult problem if it fits neatly inside one coherent reasoning episode. But long-horizon tasks, they are fundamentally different beasts. Just think about managing a massive project at work. It requires making hundreds of intermediate decisions, processing asynchronous documents written at completely different times. And crucially, you have to remember exactly why an earlier choice was made. If you discover that choice was wrong, you have to revise it and then carefully propagate that correction through everything that followed. So the challenge completely shifts from simple momentary reasoning to maintaining organized reasoning over a really extended period.
We can actually see a really clear parallel to this in human behavior. Think of working memory like a brilliant person's limited capacity to hold information. Even an absolute genius cannot keep an entire research program, a complex legal case, or a sprawling institutional history perfectly active in their working memory all at once. That is exactly why we rely on external memory. Paper, diagrams, notebooks, databases, entire organizations. External memory isn't just a convenience. It fundamentally changes the kind of problems intelligence is actually able to solve. Because once information is written down, it no longer has to remain continuously active inside one mind. It can be safely stored, retrieved, compared, and shared.
Which brings us to the structural solution for artificial systems in Section 2, the architecture of coordinated intelligence.
So instead of asking one lone agent to hold the entire problem in its head, a multi-agent system tries to create a structure very similar to human organizations by dividing the task into specialized roles. You might have a planner who organizes the long-term steps, a researcher heavily investigating the evidence, a verifier testing the reasoning and actively searching for contradictions, and a reviewer evaluating outcomes and unresolved questions. Because each agent operates within a much narrower context, its responsibility is strictly limited, and this successfully allows each agent to allocate much more focused attention to just its assigned part of the problem.
So the crucial point is that division of labor alone is not a silver bullet. If you simply throw more models at a problem without a structural framework, they very easily become a chaotic collection of disconnected conversations. One agent might make an assumption its peers never even see. Two agents might duplicate the exact same work. You might end up with several agents producing conclusions that are individually reasonable but mutually incompatible. The real value of a team definitely doesn't come from just artificially increasing the headcount of models.
That true value comes from coordination, specifically through a shared memory layer. We define this as an active, structural repository where provisional findings, verified evidence, decisions, uncertainties, and revisions are all preserved in specific forms that all the other agents can easily access and understand. This memory layer is the absolute critical piece of coordination that ensures agents know which findings are solid and which are just provisional. It's what transforms a disjointed group of models into a genuinely organized, functional system.
Let's move on and see how this builds, because this shared memory directly enables a continuous cross-checking process. See, individual reasoning errors are often very local. One agent might just overlook a crucial fact, or propose a strong hypothesis while vastly underestimating the evidence against it. But in a coordinated team, when one agent proposes a hypothesis, a peer immediately challenges it from a completely different perspective. In this architecture, disagreement isn't treated as a failure, it's treated as vital information. This continuous peer checking is exactly how a team reliably catches those overlooked facts.
Moving right along to Section 3, Rules of Systemic Coordination, because multiple agents do not automatically produce truth on their own.
The reality is, without strict operational rules, multiple agents can actually share the exact same blind spots, reinforce each other's errors, or just waste massive amounts of resources debating minor details. This is where the energetic paradigm comes in. From this perspective, the central problem is resource allocation. Every single agent consumes computation, time, memory, and verification effort. Therefore, a well-designed system has to follow strict rules. It assigns specialized work only where specialization actually creates value. It triggers additional checking specifically when uncertainty or risk is high. It aggressively preserves information whose future value exceeds the cost of storing and retrieving it. And it ruthlessly removes duplicated or outdated information before that memory becomes a source of system-wide confusion.
What this ultimately produces is a completely different understanding of intelligence itself. The strongest system may not be the one with the smartest individual component. Instead, it's the one that best organizes limited components across time. Think about it. A single model desperately concentrates intelligence inside one reasoning process. But a coordinated agent system distributes intelligence seamlessly across roles, memory, communication, and verification. It really is a triumph of architectural organization.
And this brilliantly illustrates the definitive thesis for today's explainer. Long-horizon intelligence depends on coordination, memory, and verification, not larger context alone. The systemic advantage doesn't come from making each individual agent brilliantly smart. It comes from preventing the entire system from depending on a single, fragile, limited context window. The architecture is what allows the system to preserve work, divide responsibility, recover early knowledge, expose disagreement, and successfully correct itself over time.
Which leaves us with a rather provocative final question to ponder. Will teams that become exceptionally good at coordinating many specialized agents build a lasting advantage over improvements in individual model intelligence? I mean, if system organization reliably trumps raw individual capability, what happens when we truly master that coordination? Well, that exact question is what we're going to explore in our next explainer. Thank you so much for joining me, and keep thinking structurally.